Hi, everyone. Thanks for joining. I'm Wada Mustafa, and today I'm joining my colleague, Wenyi Zhang, to talk about two open source frameworks for supporting portable SQL and UDFs between Spark and other engines. They are Coral and Transport. So in recent years, it has been mainstream for modern data architectures to support a variety of execution engines to cater for different flavors of data engineering. So for example, some engines such as Spark support a wide variety of data analytics use cases and SQL APIs, in addition to like non-SQL APIs such as Scala or Python. Also, some other engines focus more on SQL interfaces such as Hive, Trino, or Presto. And at the same time, maybe other engines support or focus more on the use case type. So there are engines that support streaming use cases or other engines that support or cater for maybe graph analytics or machine learning workloads. But also with the variety of execution engines, that entails the variety of language APIs that they support. So some of the language APIs are just different flavors of SQL, such as Spark SQL, Hive SQL, or Trino SQL, or Flink SQL. Some others can be an implementation to support a completely different syntax to support like domain-specific languages, such as Gremlin or Sparkle to support graph workloads. And some cater to users who are more familiar with functional style programming or imperative programming, such as Spark, Scala, or Python. So at the same time, modern data lakes can have their data sources be or come from a variety of data sources, such as tables or views. For example, execution engines expose adapters for supporting multiple table formats, such as the Hive table format, the Iceberg table format, Delta Lake, Hoodie, and even those table formats expose adapters to read data out of different file storage formats, such as Avro, ORC, or Parquet. At the same time, views can also be another type of data source, and they also come in different shapes and styles. So the view can have or can be defined through a variety of SQL query languages to define the view text. And also the UDFs in the view can be implemented through different view UDF APIs. But also, data sources are not necessarily only tables or views. They can be also complex SQL backends. For example, Spark can have a backend engine as a connector, and that engine can have maybe like a SQL workload or a complex SQL snippet sent to that engine, and then the communication happens between Spark and that engine through a standard API such as JDBC. And then this becomes another form of like more complex data source compared to basic tables or views. So what we're observing here is a movement towards what is known as composable data architectures, where many of the data architecture components are just pluggable. So query execution engines can integrate or be configured to work with multiple table formats, and table formats can also be configured to work with multiple storage formats. However, we're not quite there yet. For example, query execution engine is still tied to, for the most part, to certain query languages. It's also tied to specific view catalogs where it can resolve views from. Also, query optimizers are still like customized to like process and rewrite engine-specific plans. So that said, we believe that a key property of true composable data architectures is the logical interoperability. Logical interoperability entails defining a common representation for the logic that can be used to express different SQL dialects or different view definitions or different engine plan representations or different ways to push SQL down to back-end engines or different ways to process or a single way or a unified way to process engine logical plans and implement different rewrites. And logical interoperability also entails implementing a number of adapters that transform the logic from one input representation to an output representation. So such a framework is implemented through Coral that captures both SQL and relational algebra representations for logical interoperability. And on the other hand, Transport also implements the UDF aspect. For example, Transport implements a common API to express common UDF operations in a unified way through a unified data model, and also an API to express unified type validation and inference. And at the same time, it implements a number of transformations to convert a UDF expressed in that API to a native UDF to execute on any engine. So back to Coral, it's an open source project since 2020, and it extends calcite logical plan to express the logic, and the operators that collectively define the that intermediate logical representation are called Coral IR. So the way Coral works is by converting an input representation to Coral IR, which is a set of standard operators, and then converting the operators back into another output representation. So some of the currently supported conversions are converting Hive QL or Spark SQL or Trino SQL, which is work in progress, to Coral IR. And also on the other hand, or on the other side of the transformation, Coral supports converting Coral IR into Spark SQL and Hive SQL and Trino SQL. There is also a component to convert Coral IR to Avro schemas. And the way that works is that given a SQL view along with Avro schemas of base tables, that component would derive the Avro schema for the output of that SQL. So just to take a closer look at how Coral works behind the scenes, we can consider that Spark query. And the use case here is to convert it to a Trino SQL. In this query, we can see that there is a use of a function that is called inString, which is used to find the occurrence of one string in another. And also there is an array access operator with 0 based array indexes. And there is also a negation operator that is expressed in this exclamation mark. So the corresponding query to that Spark SQL query is this Trino SQL, where the function that finds the occurrence of one string in another is called string position. And the way to access arrays is through a function that is called element at. And in that case, the arrays are or have indexes that are based off 1. And there's also a negation operator that's represented in the keyword not. So the transformation happens on a two-step transformation. So first from Spark SQL into Coral IR. In this case, the inString function is converted to the Coral operator inString as well. And the array access is converted to an array access operator in Coral IR. However, since array accesses in Spark are based off index 0, and Coral standardizes array accesses from index 1, so the operand here is shifted by 1, as you can see on the right-hand side. And then the negation operator is expressed as the negation operator not in Coral. Now, the second step of the transformation takes place by going from Coral IR to Trino SQL. And in this case, the inString function is translated into the string position function, taking the same kind of operands. The array access is transformed to the function element at with the same parameters. Since in Trino, the array indexes are also based off 1, and Coral IR is also, or Coral IR arrays are also based off 1 indexes, then there is no need to shift the index anymore in this transformation. So we just convert the array operator into the element add function, preserving the operators. And the not operator in Coral is also transformed into the not operator in Trino. So what I have just shown was a simple example of like how simple transformations could take place in Coral, but Coral also supports like more complex transformations, such as lateral view joins and user-defined table functions and window functions and common table expressions. So Coral is integrated in a number of places. Some notable integrations are in Trino open source project, where it is used to support converting or like accessing Hive queries or Hive views inside Trino so that Trino can evaluate Hive views and understand the query and parse it and execute it. Also, it is integrated in the LinkedIn's fork of Spark, and that benefits basically view resolution, and like the benefits of that are accessing Hive and Trino views from the Spark engine, and enriching the data frame schema by leveraging the Avro component, because as we mentioned, there is an Avro component that transforms the view definition along with the Avro schemas of the underlying tables into an Avro schema of the view, in maintaining both the nullability and the casing of the data frames. Another value of integrating Spark, Coral with Spark is applying view schema evolution automatically, since the schema is expanded at read time, so that when an underlying table schema evolves, that view schema also evolves at the same time without having to invalidate the view. And finally, that integration helps with registering UDFs that are mentioned in the view automatically without the user having to manually register the UDF or download its artifact to the Spark session. Another integration is with the Spark Dataset API, and in that integration, like Coral is used to obtain the schema of the view, and then another component would translate that schema into Avro classes that are uploaded to an artifact management system, and users who wish to access the tables or views through a typed safe API would only or need only to declare a dependency on the artifact that's uploaded to the artifact management system, and then start using a schema for that table or view on the fly. So for more details on how that system works, you can refer to the blog post linked in the end of the slide. Although Coral is integrated to the LinkedIn fork of Spark, we're also looking into making Coral compatible with Apache Spark. And that happens through an ongoing Spark project improvement, where in Spark Jira 31357, there is an ongoing effort to make view access and resolution in Spark pluggable, meaning that the data source API can be extended to allow custom view resolutions to happen without being hard-coded in the Spark engine. And in this case, Coral can also be one of those, one of the implementations of this API, where users can just deploy that Coral extension along with regular Spark binaries, and then be able to leverage the query translation capabilities through that extension. So another way Coral can be used is in standalone mode. And in this mode, there is no need to integrate with an engine. Basically, like a user can just interact with Coral as a service, where through HTTP requests, they can set the source language and the destination language between which they want to translate, and mention the query. Then, as part of the HTTP response, the translated query would be part of that response. You can try that translation today by following simple steps on the Coral GitHub. In terms of future extensions for Coral, we plan to add new adapters to convert between Spark, logical plan representation, and Coral IR. What that enables us is not only being able to convert Spark SQL into Coral IR, but also convert any Spark language API into Coral IR as well. And that basically covers Spark Scala, Java, and Python. And by having that extension be part of the Catalyst rules, by adding a custom rule that implements this transformation between Spark logical plan to Coral IR and back to Spark plan, we can implement common rewrites, such as materialized view substitution or incremental view maintenance, to have a version of a view that can deal with incremental data updates. We can also ingest data governance operators automatically, such as operators that can filter rows or columns based on the use case. Another extension is through integration with data source APIs, specifically data sources that are more sophisticated. So for example, through the integration with the data source API, one can push complex partition functions to table formats, such as Iceberg or Delta Lake. At the same time, through an integration through a JDBC connector, the complex SQL snippets can be pushed down to a back-end engines so that they can be translated into that engine's native SQL dialect, and then the results can be returned back seamlessly to Spark through that integration. So with that, I conclude the Coral part and hand it over to Winnie to talk about transport.
Thanks, Wala. Hi, everyone. My name is Winnie. I will continue to talk about the transport. So transport is a framework for user to write performant UDFs. The idea is to implement logical ones and run it on multiple engines as native UDFs. It is motivated by the fact that SQL has pretty well understood IR, which is region algebra. It has standard operators such as scan, fill, project, join, group by. But for UDFs, they do not follow this pattern. Like they are opaque, they use imperative language, and they are not portable or translatable. Looking at the current state of UDF API landscape, we noticed that there's a phenomenon called UDF denormalization, which means that UDF needs to be implemented multiple times to achieve interoperability. UDF denormalization comes with several issues. There's duplication, meaning that there are multiple versions of the same UDF. For example, one for Spark, or one for Trino, one for Hive. It's not clear which one is the source of truth. There's inconsistency. The duplicate implementations can diverge, causing data inconsistency. There's low productivity. Developers need to learn multiple APIs, and they need to implement the same logic multiple times using multiple APIs. And there's no performance. In some cases, need to use a tuple conversion adapters to enable portability. Let us take a look at how UDFs are implemented in Hive and Trino. So to implement a Hive UDF, users need to extend a generic UDF Hive abstract class. And they need to write imperative code to do type invalidation and inferences. However, to implement the Trino UDF, users need to use special annotations to indicate that a class represents a UDF. And they need to use a type signature to define expected returns. From previous examples, we can see that the APIs are complex. They expose low-level details of engines, and the data types may not intuitively map to like SQL type systems. In addition, the APIs are different across engines in terms of what to expect from developers and what the features they can provide. Transport APIs are simple and consistent across the engines. In high level, like Transport provides a standard UDF API for users to define UDF, and a standard data API to operate on input and output data. Let us take a look at one Transport UDF example. This UDF is called map from two arrays. What it does is to convert two arrays into a map using the elements from the first array as keys and using like the elements from the second array as values. In order to implement UDF using Transport API, user need to define in these 4 parts. In the first part, user need to extend std UDF2 class. This is the abstract class expressing that it takes 2 input parameters. In this case, it takes 2 std arrays and it output a std map. The type validation and inference are defined in the second and the third part. The actual logic is implemented in the fourth part inside the inval method. In this case, it is straightforward. Basically, it iterates through 2 arrays and output a map. So from previous Transport UDF example, we can see that there's no engine specific details, and the user can focus on the logic. Now user has implemented the UDF, how to use it in multiple engines. Transport comes with a Gradle plugin, which will generate the UDF jars automatically, one for each engine. All user need to do is to run a Gradle build, and the Transport framework will take care of everything. So behind the scenes, the Transport plugin will perform code analysis and use metadata to generate engine-specific wrappers. And then those wrappers will be compiled and packaged into the UDF jars, one for each engine. So this way, Transport UDF serves as the intermediate representation of UDF logic across engines. It has 2 engine-specific phases, which are provided to user automatically by the Transport framework. One is engine-specific auto-generated wrappers. Those wrappers are for engines to call as native UDFs. The other is engine-specific, engine-specific date and types implementations. The implementation enables the UDF to interact with engine native data type systems. So in conclusion, with Transport API, there are several nice features. It is simple, meaning that a user can focus on the actual logic. No need to deal with engine-specific details. It is a feature-rich. It supports declarative type signatures with generics. It also has get required file support. Most importantly, it's translatable. UDFs can run on multiple engines as native UDFs. Code specific to each engine is auto-generated. Last but not least, it is performant since it has a direct access to the native engine type systems. So basically, no data object conversion needed here. Both Coral and Transport are open source projects. We welcome contributions and collaborations. Feel free to submit a pull request on the GitHub. This is what we have, and thank you so much for joining us today. With that, we will proceed to Q&A.
For the open source project, have you guys considering incorporating some of those non-standard SQL, like the one the one in New Relic or Grafana? Their SQL actually it doesn't support join. The join operation is actually like a union or union or operation. And what we encounter is all the software engineer, they are very accustomed to the non-standard SQL. So when they create some data or dashboard in those systems to translate those non-standard SQL to standard SQL is a very painful process. So I was wondering, do you guys have any roadmap to incorporate some of those like very, very non-standard SQL, like NRQL, like Grafana, and then like Couchbase, they also have their own 1QL. That's also like a non-standard SQL.
Yeah, so as long as the SQL has some algebra that backs it up and can be reasoned with using algebra, I think it is still convertible to Coral IR. And the stance there is that as long as you can convert that SQL into Coral IR, then you shouldn't worry about the rest of the pipeline. So you can have it converted to any representation that's already supported on the left-hand side of the conversion. So I'm not quite familiar with like flavor of SQL you're referring to, but there are also APIs in Coral where you can plug in your implementation so that you can start from your own SQL and get to Coral IR, and then let the rest of the pipeline do the rest of the conversion.
So for the API, we have to deal with both ends. Let's say I already have some sample that transfer those non-standard SQL into a SQL that's supported by either like a Presto or Redshift. So would that information help you guys if we have this kind of a side-to-side comparison SQL already? Like when we're using the API, I'm not quite sure what can your API do.
Could you come closer? Yeah.
So we have sample already that kind of translating those non-standard SQL to a Redshift SQL code. And then with this kind of example, can we kind of contribute to this open source project? This type of request?
Yeah, we're open to contributions, of course. Like, what is the dialect that you're referring to in this case?
Huh?
What is the non-standard SQL in this case? What is the dialect?
It's a SQL that developed by New Relic. They call it NRQL. And then like they don't have group by, they have this thing called faucet. And then they have this time series feature that you, instead of like, you have to use like a time series minus something. So it's like a really weird flavor of the SQL.
Yeah, I think something like this would depend on the appetite in the community or like the degree of adoption of that flavor of SQL. So it might make sense to have it as part of the main repo if there is like large adoption of that specific dialect. But if not, I think it's always possible also to have it as a plugin by implementing a number of APIs.
I see.
Yeah.
Thank you.
But we can always discuss that. Yeah.
Have you thought about potentially porting some of this to Spark specifically? I'm also a Spark developer, so I'm curious if you thought about having Spark adopt the transport API directly. I don't know if that's out of the question or not. And then my second question was, how much adoption have you had from the project so far for the transport UDF specifically?
I couldn't hear the question due to the mask. I'm not sure if you.
Yeah, a little bit unclear.
Yeah.
Sorry. So the first question was, so the transport UDF API, have you thought about having an engine like Spark implemented directly so that they can just use transport API directly instead of having the Hive UDF extension and all that? And then the second question was, how much adoption have you had for the transport API?
So the question is, have we thought about implementing a version of transport that supports Spark native UDFs instead of Hive UDFs?
Yes, exactly.
As a bridge to work in Spark?
Yes.
Okay, you want to take that?
Maybe you can go ahead.
Okay, so indeed, the Spark implementation of transport is actually a native implementation to Spark, and it doesn't use Hive UDFs in this case. It uses the expression API as the back end for the transport UDF. So any transport UDF that's implemented in this API would boil down to at the end of the day to an extension of the expression class, and every transformation that you do as part of the UDF translates into operations on Spark internal rows directly.
Yeah, and that's kind of another thing. I work for NVIDIA, so we have a columnar plugin for Spark. And so it would be nice to have support for columns, but that could be a feature. And that's kind of my question for the adoption, like how much adoption have you had?
Right, so we don't support columnar batches yet, but yeah, we do internal rows.
Thank you.
Thank you so much.
Thank you.